In this lesson, we will learn how to encode text in a computer. So in previous lessons, we explored how to encode numbers in binary. Now we're going to take that method one step further and look at how we can encode text with a binary representation. So hopefully you are beginning to realize that if we can figure out a way to represent information as a set of numbers, then we can encode it in bits and store that information in a computer. So how would you encode text? For example, how would the text on this slide be saved in the computer if the computer could only store information as zeros and ones? If it were up to you, how would you encode text in binary? So either in a breakout room or on your own, I want you to come up with a scheme for encoding text. How would you encode the word hello using your scheme? So either assign one person to share out as a comment on this slide, or individually share your scheme as a comment on the slide. So look at everyone's schemes, and were the schemes exactly the same? How many bits does your encoding scheme require? So for example, how many bits would you need to say hello? And did you account for anything besides the letters of the alphabet? Of the encoding schemes that were posted on the slide, which one is the best, do you think, and why? So these are just some questions to consider. Well, it turns out there's a standard encoding for most of the symbols you can type on an American keyboard. So if you look at your keyboard, anything that you can press, like the asterisk, the H, the backslash, the question mark, those can be encoded in the computer. And we do this with an encoding scheme called ASCII, which stands for American Standard Code for Information Interchange. And so there's a table that maps all of the keys on your keyboard to a decimal number. And then that number is stored as binary in the computer. If you did a Google search for ASCII, a table like this would appear, and this maps all of the characters on your keyboard to a decimal representation. So you can see the arrow is pointing to the space key. So if I hit my space bar, that's encoded as 32 on the computer. And notice there's a different encoding number for uppercase A and lowercase a, right? Because they are two different characters, and so they have to be encoded differently so the computer knows if you're typing an uppercase A or a lowercase a. So I want you to decode the following binary message and then post your answer as a comment on the slide. So first you're going to have to take each byte, which is the 8 bits, and convert it to decimal, and then look up that decimal number in the ASCII table. So go ahead and pause the video, decode the message, put it on the slide, and then return back to the video. So ASCII codes were originally only 7 bits long, so there were 128 possible values. That's why you see 128 values, 0 through 127 in the table. So the first 32 are control characters, and they mostly go unused. But 32 through 126 are the printable characters. They include all the digits, 0 through 9, all of the letters, all 26 of the letters, both uppercase and lowercase, and many of the common punctuation symbols. And then 127 is the symbol for delete, because when you hit the delete key on your keyboard, the computer needs to know what to do with that, right? So 127 is the decimal representation for delete. But over time, 8 bits became the standard chunk size for encoding information, and ASCII made the transition to this 8-bit encoding by simply adding an extra 0 in front of the old 7-bit codes. So look at this picture below. This conversation is on a smartphone, which is a computer, between two people using text messaging. And so we can see the characters on the screen, but what's hidden? What are we not seeing? So go ahead and just think about that. And what's hidden are the ASCII characters, right? When you look at your phone and your text message, you're seeing the characters. Hi, Leonte. How are you liking CS 160? ? But the computer doesn't store those letters as letters, right? The computer is storing those letters as ASCII values. So when we don't have to think about this layer, we call that an abstraction. But really, every text message that you receive is just a bunch of zeros and ones. And then the smartphone displays it as the characters that we can represent as text. So what is another example of abstraction from your everyday life? Something that you don't completely understand how it works, but you can still use it with confidence. And I'm going to give you one example. Like when I'm driving my car and I push the gas pedal, there's a lot going behind that, right? The gas goes from the gas tank and goes into the engine, and I don't really understand anything how that works. But I know when I press that gas pedal, the car is going to go forward. Okay, and so all of that detail of what's happening in the engine to turn the wheels is abstracted. So go ahead and think of a different example of an abstraction and post your thoughts as a comment on this slide.